Let's look at how electrical energy works in a circuit. When charges flow through a circuit, they lose electrical potential energy. You've learned that energy cannot be created or destroyed, so the lost potential energy must be transformed into some other form of energy. Depending on the circuit component, the electrical energy might be transformed into heat, light, kinetic, and/or sound energy. In the case of a light bulb, the energy is transferred into heat and light energy. The heating effect of an electric circuit is due to the collision of the delocalized electrons with the positive metal ions as the electrons move through the crystal lattice. These collisions cause the metal ions to vibrate more vigorously, so the electrical potential energy of the delocalized electrons is effectively transformed into internal energy in the form of vibration of the metal ions. This energy transformation is readily recognized by a rise in the temperature of the conductor. The work done per unit charge, better known as voltage, is given by the equation shown here. Potential difference is equal to the work done divided by the charge. The equation can be rearranged to work is equal to the charge times the potential difference. Since charge is equal to the current times the time, we can substitute for charge in the equation, which gives us work is equal to the potential difference times the current times time. Potential difference is equal to current times the resistance, so again we can substitute, giving us the equations where work is equal to the current squared times the resistance times time, or work is equal to the potential difference squared times time divided by the resistance. Now, we don't have to know where all the equations come from, just know that current, voltage, resistance, and time can be used to calculate the work done in a circuit. The unit of work or energy is the joule. All these equations still calculate work and in joules, J. The only difference is the information you have to calculate with. Since V is determined by the power supply and is therefore constant, the heating effect of an electric current depends on 1. The strength of the electric current, 2. The resistance of the conductor, and 3. The time for which the current flows. The greatest heating effect therefore takes place when the current is large, and thus for a given voltage the resistance must be correspondingly small. Joule's law states that the amount of heat generated in a conductor is directly proportional to the square of the current flowing through it, directly proportional to the resistance of the conductor, and directly proportional to the time for which the current flows. Each of these parts of Joule's law can change the amount of energy being given off. The expression work equals I squared times R times T is known as the Joule's law equation. The heating effect of an electric current is used to advantage in filament bulbs and the heating elements found in appliances such as stoves, kettles, toasters, and geysers. The heating effect of a current also results in energy losses in many devices, whose primary function is not heating. For example, transformers and motors experience energy losses because they get hot during normal operation. Heat losses can be reduced by using smaller currents, and it's for this reason that very high voltages are used to transport electricity over overhead power cables. The relation can be expressed graphically. Remember that direct proportion graphs pass through the origin and are straight line graphs. Let's now have a look at power. The power in a circuit is the rate at which the electric energy is transferred. The power of an electrical appliance is given by the following expressions. Power is equal to the potential difference times the current. Or, power is equal to the current squared times the resistance. Or, power is equal to the potential difference squared divided by the resistance. The unit of power, the watt, is therefore equivalent to the potential difference, volts, V, times current, the ampere, A. The relationship between work and power is shown by the equations. If this all looks very confusing, don't panic. All you must do is look at the information given to you and choose between the first, second, or third equation. Electrical potential energy is supplied by Eskom in South Africa. The municipalities deliver a monthly account, charging those homes for the electrical energy that they've used. Somewhere on the account will be a charge for the number of kilowatt hours of electricity that were consumed. We can do an energy audit on our appliances by looking at the ratings supplied on the labels. Kilowatt hours and joules are two different units of energy. We can find the relationship between the two units by expressing kilowatt hours in the normal SI units. Let us now look at some questions involving work, energy, and power. In the diagram we're given electrical devices, X and Y. They're connected to a 24-volt battery with internal resistance R as shown in the circuit diagram. The power rating of each of these devices, X and Y, are indicated in the diagram. With switch S1 closed, the devices function as rated. The next question asks, calculate the current flowing through resistor Y. Here we have the power, 150 watts, and the potential difference of 20 volts. Thus, using the power equation P is equal to V times I. Substituting in, 150 is equal to 20 times I. Solving for the current, we get I is equal to 7,5 amps. The next question asks us to calculate the total resistance of the external circuit. First, we need to add up the currents from the parallel branches to get the total current. This current external is equal to 5 plus 7,5, which gives us 12,5 amps. Now we can calculate the resistance, remembering that voltmeters in parallel are equal. Thus, resistance is equal to potential difference divided by current, which is equal to 20 divided by 12,5, and of course this equals 1,6 ohms. The next question asks us to calculate the internal resistance of the battery. Here we can calculate the internal potential difference by subtracting the potential difference of the external circuit from the EMF. Thus, 24 minus 20 gives us 4 volts. Now we can calculate the internal resistance by dividing the internal potential difference by the current. Thus, 4 divided by 12,5 is equal to 0,32 ohms.